Hello and welcome to VLSI Design Lecture 7, and we're going to continue with our physical operation of a MOSFET. And in our previous class we have already induced the channel. As you can see, this was a channel that we induced in our last class, and today we are going to continue from the same point. Okay, so we had applied a positive voltage across gate, and both source and drain are grounded along with the body terminal. All right, so with the help of that we have already got the channel, and the length of the channel is depicted with L. Okay, capital L. So now, how did we get the channel? First we applied a small negative voltage, then we applied a small positive voltage, then we kept increasing the small positive voltage at gate, and that's how we got it. Okay, now at this point, when we have kept increasing our VGS in a positive way, we kept it increasing. What happened was, the electrons from the substrate and the electrons from the N plus pockets have come to the surface of the substrate and occupied this place. Okay, and occupied this place, and because of that, what happened? The surface of the substrate inverted. Why are we calling it as inverted? Because it's a p-type substrate. P-type means majority are holes, positive charges, and minority are electrons, the negative charges. Okay, so this place has been occupied by negative charges, isn't it? And this is completely negative, this portion that we are calling it as channel. And at the gate, what kind of voltage we have given? An increased positive voltage, so the voltage around here is positive, this side is negative, isn't it? And between this positive and this negative, what do we have? We have the oxide layer. So what does this actually look like? A parallel plate capacitor, where the top plate is positively charged and the bottom plate is negatively charged, and in between these two plates we have something called as the dielectric. Okay, so we have the positive charges at the top, we have the negative charges at the bottom, and in between this we have the oxide. So our MOSFET here behaves as a capacitor. And whenever we have a capacitor and it's turned on and functioning, what do we get? We get an electric field. In and around our capacitor. So this is the MOSFET, isn't it? So the top plate that is near the gate is positive, the substrate is negative, surface of the substrate is negative, and we have the oxide. So over here as well we will have an electric field, and the direction will be bottom to top, like this. Okay, the electric field's direction will be from bottom to top. And if you remember, in our initial classes I had discussed the full form of MOSFET, and this E stands for electric field. Okay, E stands for electric field. So this is the electric field that we had spoken about in our initial classes. And sorry, not the E, it is the F that stands for the field, and the E is its effect. So as and when we keep on studying, very soon you will understand what is the effect of this electric field. Alright, now so our MOSFET at this point starts behaving like a capacitor, and it will keep on behaving like a capacitor because we are never going to turn this VGS equals to 0. Our VGS is required to keep this MOSFET on and working. So VGS will be a constant. You have to keep the VGS connected to the MOSFET, otherwise your whole device will turn off. Okay, so in all the functionalities you will have this electric field in our MOSFET. Now second point to observe, okay, that our VGS, because of this VGS only we got the channel, isn't it? We got the channel because of the VGS. And how did we get? Simply we randomly gave one kind of voltage like 5 volt or 9 volt and we got the channel. No, it doesn't work like that. We kept on increasing the positive voltage around the VGS, and that's how we, at a particular voltage, at a particular value, we got the induced channel. So the moment the value of VGS is equal to a particular value which then got us our channel, we will call that voltage level as Vt. We will call that voltage level as Vt. Now you need to remember that V, and in the subscript it's a small t. That is our threshold voltage. Always remember it's a small t, not capital T. That is also a significant thing. Okay. So what is this threshold voltage? If somebody asks you for 2 marks, then you should say it is the voltage at which the MOSFET gets an induced channel. Okay, the keyword here is induced. Okay, so these are the 2 points that you need to know. Okay, now if I keep on increasing, so at this particular voltage my channel was induced. Is this channel very strong? Is this channel very sturdy? Of course not. It's just the initial point at which it began. Okay, it's just an initial point at which it began. So if I have to make my channel strong, if I have to make my channel, a better channel, okay, how will we do that? We keep on increasing our VGS so that it is greater than equal to Vt. The minimum condition over here is VGS is equals to Vt. That will also work for us. But I want my channel to be strong. Okay. So how will we do that? By keeping on increasing VGS such that we follow this condition of VGS greater than equals to Vt. Okay, so that is how our channel will get strong. Now why am I saying that if I keep on increasing my VGS greater than equals to Vt, my channel will be strong? How the channel will get strong? It's simply a voltage, right? The channel is formed of electrons, isn't it? The channel is formed of electrons. From where did we get these electrons? From the N plus pockets and the substrate. Okay. So if I keep on increasing the positive voltage at gate, more electrons will be attracted towards the surface. More electrons will be attracted towards the surface. So what will happen if we keep on doing it? More number of electrons get attracted to the channel, and hence we can say that the channel has become strong. So a strong channel. So this one, just gets me the induced channel VGS equals to VT, and if we maintain this condition of VGS greater than equals to VT, we will get a strong channel. We will get a strong channel. So in other words, I can say that the previously made channel and this current channel, what is the difference? That my channel has enhanced. So it means channel is enhanced. And remember, I told you that there are two types of MOSFET, enhancement type and depletion type. And why is it called enhancement type? We will get to the point very soon, and this is the point that I was talking about. So this is how the name of this MOSFET has become enhancement type. Why is it enhancement type? Because the channel gets enhanced. Because the channel gets enhanced. Okay. So whatever I have discussed over here today, okay, whatever I have discussed here today are very important, very small but very important points for your Viva or the short questions that you get asked for 2 marks, isn't it? So for those things, these points are very important. Or you're appearing for some VLSI job interviews, MOSFET is the basic building block and they will be asking you that. Okay. So now we have got our channel, we have got our electric field, and we have enhanced our channel as well. Now let's see what else we can do. So point number C. So here I have written as point number C, and it's a continuation from our previous class wherein we discussed point A and point B. If you want to, refresh it or you missed the class, I'll be listing out the playlist or the course from where you can check those out. Okay. So now point A, point B have been covered. It's time for point C, and what point C says? That we are going to do some things, we are going to apply some other kind of a voltage. And what is it? VDS. So VDS means, see, remember one point, our source will always be grounded and body will always be grounded. So what are the two terminals left out? Gate, wherein we applied VGS, got the channel, enhanced it. The other terminal that is left out, that is our drain, and in this point we are going to see a voltage named VDS, So VDS means source is always grounded, voltage is actually applied at the drain end, and the voltage difference is taken as VDS. Okay. So this is our diagram. So at this point we simply had the channel. Since we have applied VDS, I have denoted something extra in our diagram, that is the flow of ID. Why? Let us see. Okay, so now we are applying a small positive VDS at drain terminal. Okay. We are going to apply a small positive VDS at drain terminal. So what will happen is, see, gate voltage is increased and is maintained. So the first condition is that VGS is greater than equals to VT, and we are going to make it a constant. We are not going to fluctuate this voltage again. We are not going to touch it again. We are done with it. Okay. So this becomes one of our conditions, the primary condition for coming up to step C. Okay. So small positive voltage is applied at the drain terminal. So what happens? Source is grounded, VDS is applied, and we have already turned on our MOSFET with the help of gate VGS. Okay. So what will happen? Of course, one end is at 0 volts and a small positive voltage is given at point B. What will happen? Current will flow. Now current flows from this side, so of course the flow of electrons will be on the other side. Okay. So that is how, and since it is flowing from the drain end, it is termed as ID, and the denotation is small I, and in the subscript it is written as D, capital D. So this current that is flowing in our MOSFET, okay, it depends. Now from where to where it is flowing? It is flowing from the drain end to the source end, and from the source it is moving into the ground. Okay. Now via what it is flowing? This drain and source are done, but it is flowing through this channel, the channel we have created in our previous step. So it is flowing through the channel. Now the channel is made up of what? It is made up of electrons, and that is why we are getting the flow of current. So this ID, the flow of ID or the magnitude of this current depends on two things. It depends on directly proportional to the amount of current flow. The amount of current flow is directly proportional to the excess voltage at gate. That means we have to have our voltage greater than the threshold voltage. Only then our current will flow properly. Okay. So this is the first condition. For ID, the amount of current. Okay. And ID, or the amount of current that flows from drain to source, also depends on the level or the amount of VDS you are applying. Of course, it's a valid point, right? There has to be a voltage difference between point A and B for the current to flow. So it also depends upon the amount of VDS you are applying. So these are the 2 points based on which the amount of current is based on. Now, why are we discussing this? Of course, do we need a minimum current flow? No, right? Our output is our current. Okay? Our output is our current. So I want my MOSFET to give me a better output, isn't it? If we are doing an experiment, we don't want a device to give us the minimum amount of output. We want a good output which can be define that yes, whether the device is working according to our desires or not. Okay. Now if I have to plot this, how this dependency actually works, on the y-axis I will take the current flow, that is ID, and on the x-axis I will take VDS. And we will see the dependency. See, there are two direct proportionals for ID, right? VGS minus VT. So this is also called as excess voltage. One another term that we have to remember. Okay. So if my channel is not formed, means what? That my device is only not on. If the MOSFET is not on, will it give you any kind of output? No, right? So when VGS is less than equal to VT, don't take equal to, VGS is less than VT. At that time, will we get any kind of output? No. So that is why our current is on the x-axis, means it is completely zero. So this is also, so what happens over here when VGS is less than VT? That is infinite input impedance. Impedance is nothing but resistance, another word for resistance, so no need to get confused. Okay, so when VGS is less than VT, infinite input impedance. if the resistance is infinity, will you get any kind of current flow? No. So that is why at this point our current is on the x-axis. Now, if the excess voltage is VGS, I will use another color, so it's VGS minus VT equals to 0.5. So this is a very minimum kind of difference between the two voltages, VGS and VT. So I'm taking that point where if we are doing this, then we will have slight amount of current flow in our MOSFET. Okay. Now, if I keep on increasing, now let's see, I want to check what happens if I increase this difference, VGS minus VT equals to 1.0 volts. Okay, so now I have increased the difference, so my current flow has also increased. It is directly proportional, right? So I have got an increased output. Okay, now let's suppose I want to increase the difference a bit more. Okay, so VGS minus VT is 1.5 volts. So logically what will happen? My current flow will increase a bit more, and so on and so forth. So the more you keep on increasing the difference between VGS minus VT, your current flow will increase. Your current flow will increase. Okay, so this is one of the graphs which is very important but very easy to understand. See, now you have no confusion over here. But if directly you look at this graph without any prior knowledge, you might get scared. So this is one of the few graphs that we have with the VLSI, and it's very important and very easy to understand. So now we have applied VD and we have got the current flow. Okay. Now, one question might strike you that our channel, let this be the source side N plus pocket, let this be the drain side N plus pocket, and we are talking about the channel. Okay, so this is our channel, and I am saying that over here I have given a positive voltage, this side is 0, so and this side also we have VGS minus VT, which is required to get this channel. Okay, so now I am telling you that current flows from drain to source. So electrons will flow from source to drain. Okay, and current is flowing with the help of this channel. Now you might be thinking that why do we need this channel? Why is the channel required? If I am simply providing this positive drain voltage, simply because of the voltage difference only, our current should flow. But that doesn't work work over here. Why? Because I'll explain it in a practical way. Okay, let's suppose this is you. Okay, and let's suppose this is your best friend. You are in India and your best friend is, let's suppose, in USA. Okay, so now let us have India and USA over here. Okay, you both are in different countries. Okay, or if your best friend is not outside of the country but in a different city or a different state, that also works. Just try to understand what I'm saying you. So now you're not able to communicate and your best friend is also not able to communicate with you because of long distance. Okay, because of long distance. Now we have this WhatsApp or some other social media platform or Insta or Facebook or simply telecom, with which you are able to either directly, go for a voice call, or you can go for a video call. So it doesn't even matter if you are separated by distance. Because of this technology, what happens? A bridge has formed you two. A bridge has formed between you two, and whenever you are free or your friend is free, you are able to communicate with that person, and your distance, although it is there, but with the help of this bridge, it seems small, or it seems negligible, or it seems that if you're on a video call, you will see your best friend, near you. So at that point, this bridge has helped you reduce the distance. Now, in a MOSFET as well, see, in a MOSFET as well, if I remove this channel, if I simply remove this channel, okay, if this channel is not there, what is there between two n plus pockets? What was there? P-type substrate. Was there any kind of bridge between these two pockets? No. So to create that bridge, we have done this channel induction, and because of which our current can flow. So that is why the channel formation is one of the important steps, without which you are not able to get your desired outcome. And what is our desired outcome from a MOSFET? ID. Okay. And another point that we had discussed previously, that a MOSFET is a voltage controlled device. So that will mean the output is current and input is voltage. Okay. So remember these points. Once you get to understand the concepts, you don't need to mug up any point in VLSI. Okay. So it might seem that, okay, if I just mug it up, voltage control device and whatnot, the next question in your viva will be, what do you understand by that? What is the output? If it's a voltage control device, then what is the output? What is the input? How is it? Then they will ask, how come you are getting this current as output? So for that, you need your concepts to be strong. So I would highly recommend to be, follow the playlist that I will add in the description, or you can visit my page. You'll get the course directly on the home page itself. You don't have to search for it as well. So keep on understanding the core concepts, and VLSI is easy, it's interesting, and you will fall in love with it. So that's it for today. See you next time. Have a nice day.